Hi, so today we're going to be talking about SN1, SN2, E2, and E1 mechanisms, substitution and elimination, essentially. Let me just share the screen right here. All right, so first we have an SN1 mechanism. This is just a basic sort of demonstration of the mechanism. It's not specific or like an actual example, just a basic to get an understanding of the mechanism. R's are going to be carbon groups, carbon-based groups. The X is actually an alkyl halide, and the NU is the nucleophile. So here we can see the leaving group, or the alkyl halide, or the electrophile, or the substrate. The X has lots of names. It leaves first in this type of mechanism. That is the rate determining step, the slow step. Next, we form our carbocation intermediate, and the nucleophile's lone pair wants to attack that carbocation intermediate, forming our substituted product, a nucleophile in place of the electrophile. In SN1, it's two steps. The one is for unimolecular, and the alkyl halide preference is going to be tertiary, then secondary, then primary. Primary mainly being unreactive, methyl not even being in the question. So for all of the mechanisms we talk about today, leaving groups are important. Needs a good leaving group in order for it to leave, because in most of these cases, it is the first rate determining step, so it leaves by itself, or it happens simultaneously. But either way, the leaving group needs to be good to be on its own, is how you should think about it. So to the left is just primary, secondary, tertiary substrates, ours again being carbon-based groups. Tertiary, as you can see, it has a lot going on. It is very bulky, big, group. So in this case, it doesn't matter because it's going to be, and the R groups, pause. So it's going to be planar in our case. So it's not really worried about the steric hindrance here. The nucleophile attacks the carbocation intermediate, as we saw in the last step, and they're trigonal planar. So three alkyl groups actually stabilize the carbocation. So that's why it's good in our case. Next, the nucleophile preference and rate law. Rate is just going to be K by the alkyl halide or electrophile or substrate. That's the rate determining step. Does have the nucleophile happen in a second step. So it's not just the one step, it is two steps, even though the rate only has one step in it. It's just that's the rate determining step, the slowest step. So SN1 also prefers a weak or an uncharged nucleophile. So an example, like how you figure out if it's weak. Well, uncharged or charged, you can see the strength of a nucleophile is actually parallel to the size of atoms. So on the periodic table, as we can see up here, its size increases going down, increases going from right to left. So that's pretty much the strength of the nucleophile. Those are just a few common weak nucleophiles that we're going to see. Next, for SN1, solvent preferences. We have polar aprotic, polar protic. Both are polar, like dissolves like. That's common. We learned that way back when. So here are some examples of polar protic solvents. Water, very common one. Protic, because the solvent can serve as a source of protons, stabilize cations and anions, cations being the carbocation intermediates, which is what we create in SN1. So this is good because we need that to stabilize the intermediate. That's why we need polar protic solvents. Carbocations can also be resonance stabilized. So if, allyl or benzyl, those are resonance stabilized. Those are good as well, as those are also different types of alkyl halides. So tertiary, secondary, primary, alkyl, benzyl. If it's resonance stabilized, it just forms more readily. So a leaving group in the benzylic or allylic positions will generate resonance stabilized cations when the leaving group leaves. That's why we kind of touch on it because it's benzylic, allylic. We don't focus too much on it, but it is resonance stabilized. That is why it's important. The stereochemistry of SN1 is 50-50 inversion and retention of configuration, which is known as a racemic mixture. Here I give an actual example. So we see chlorine has the chiral center with the little asterisk there. Originally, it's going to be an S configuration. Then we're going to go ahead and attack it from either side. And that's where we get inversion and retention. This is if it is chiral and because the nucleophile attacks from either side. Like we had before. Next, we have an SN2 mechanism and an SN2 mechanism. This is also just a generic form. We do have a transition state here, and it is going to have to be 180 degrees from the nucleophile to the halide. So we see SN2, the 2 bimolecular, but it only happens in one step, so simultaneously. And the nucleophile is going to attack that carbon while the leaving group leaves the alkyl halide. Then we're going to form this transition state of nucleophile to the carbon to the alkyl halide, which then, as you can see, substitution, the nucleophile substitutes for the alkyl halide. So very similar, it just happens in one step versus two, and there's not a carbocation intermediate formed. Here we go, one step bimolecular alkyl halide preference is going to be methyl. This is the only one out of the 4 mechanisms that's going to prefer methyl, and this is because of the steric hindrance that we talked about before. So tertiary, really just not reactive at all. Primary is better because of steric hindrance. So there's so much going on over there. It doesn't really want to deal with that. It already has to attack, and then the other one has to leave. So the nucleophile can't really get into the leaving group area with all of those clouds around it. That's why it is the way it is. Nucleophile preference and rate law. So this one wants a strong, good nucleophile, usually charged. And the rate is alkyl times nucleophile and the nucleophile. So it wants a good nucleophile because a nucleophile is a part of the rate determining step. So again, just the same type of chart as you go from right to left, size increases, the strength increases, top to bottom, size, strength. These are pretty common, strong nucleophiles. If it's charged, it's strong. You also look at the trend. Sulfur tends to be really strong all of the time as well. So solvent preferences for SN2 and stereochemistry. So just polar aprotic solvents. And an aprotic solvent, it does not have a proton on the electronegative atom. So it essentially takes away its shell. And this shell sort of kind of keeps everything away. So the solvent shell, it holds back the nucleophile from doing what it needs to do. So essentially, aprotic solvent dissolves that away. So it's able to react much better, much faster. And it needs to be polar to dissolve the nucleophile, as we talked about before. And essentially, if you don't have a solvent shell, then you're going to be able to react all the time, whenever. These are really common ones to know. Stereochemistry, 100% inversion, so it doesn't really retain anything, it just inverts altogether. Next, it's going to be the first of our 2 elimination mechanisms, so an E1 mechanism. Same idea as SN1, 2 steps, unimolecular, that's what the 1 stands for. This is also just a very generic. These are going to have multiple products, E1 and E2, multiple products, maybe 1 or 2. There's a major and a minor, maybe 3 or 4, depending. So first, 2 steps, rate determining step, the alkyl halide leaves. Next, instead of using a nucleophile here, we use a base. And this base is going to attack the hydrogen or the proton, and the proton's going to go down to the carbocation to form that double bond. Elimination is taking away one bond, creating a double bond. Elimination always creates double bonds. Then we have our major versus our minor product, Zayseb versus Hofmann. Now we're going to go more in depth in all of that right now. So, substrate first. Also, tertiary, secondary, primary. The only one that's different was SN2 with the opposite, so methyl, primary, secondary. All the rest, they don't really mind about the steric hindrance. So here it is again, just to remind you, and 2 steps, unimolecular. The base preference and the rate law. It wants a weak base. The rate law, it's only really about the alkyl halide. The base isn't involved in this one. That's why the weak base doesn't really matter. It does compete heavily with SN1. So the leaving group leaves. You use a base to form the pi bond. Some bad leaving groups. OH is a bad leaving group. There's a few other bad leaving groups. And honestly, all bad leaving groups, because as we said at the beginning, it needs to be a good leaving group for any of these to take place. But even if it's a bad leaving group, we just have to protonate it first with an acid or a proton. So this one competes heavily with SN1. We said that. Solvent, stereo, and regiochemistry. So the regiochemical outcome of these reactions prefers Zaysef over Hofmann products, as we talked about briefly. So that's substituted or substitution, as you can see in this picture that I drew. So monosubstituted means the double bond is connected to one carbon or carbon-based group. Di, 2, tri, 3, tetra, 4. Zaysef is favored 9 times out of 10. That's the most substituted product, is going to be Zaysef. It's going to be the major product. The Hofmann product is going to be less substituted and less favored, the minor product. Regio, just where it's at, what region it's in, which in here it's cis or trans, that's stereochemical, regiochemical. Generally prefers trans. And then region generally prefers tetra or Zaysef product. E2 mechanism, similar to SN2, elimination mechanism, also forms a pi bond. Here we have all of it in one step, and there's 3 arrows here, unlike our SN2, which only has 2 arrows. So first, our negative charge will attack hydrogen. Hydrogen will go down to form the double bond, and the leaving group leaves. And I know I said and, but this is all actually happening simultaneously in one step. Then, as you can see in our transition state, it's dotted lines wherever it's going, anti-periplanar. That's how they have to be, anti-coplanar. Then we have a major and a minor product, which is based on Zaysman. Oh, I mixed them together. Zaysef and Hofmann products. So more substituted major, less substituted minor products. They both still happen. The alkyl halide preference here is going to be, once again, tertiary, secondary, primary. Only one that differs is SN2. This is one step also. The 2 is for bimolecular. No steric hindrance here or anything. E2 base preference. So both eliminations use bases. Both substitutions use nucleophiles. The rate is going to be the K by the RX, alkyl halide, and the base. The base preference here, not her, here, typo, gotta fix that, is only strong, big, bulky bases. And then remember our antiplanar geometry. These are some examples of strong and bulky bases that we need here. Let's see. Oh, yes. So a side note, more of an exception for E2. As I said, Zaysef is always favored, the more substituted. However, when using a bulky base, the Hofmann product is actually favored in this case. So the solvent stereo regiochemistry of an E2, it can either have protic or aprotic. The regiochemistry here, it has to do with the beta hydrogen. So like we said in this part, the anti-periplanar, it takes the hydrogen. The hydrogen connected to the bromine is alpha. The ones around it are going to be beta. So it takes a beta hydrogen essentially. And multiple beta hydrogens give multiple products. We can have, minor or major, but they give multiple products. The beta hydrogens must be anti-coplanar or periplanar to the leaving group, especially in cyclohexanes, transdiaxial. If only the beta hydrogen is anti-periplanar, this will determine the stereochemistry. Cis versus trans, which is the E versus Z, but we won't really get into that. Bulky bases favor Hoffman's. And that is all we have. So thank you. I'm going to stop sharing. And thanks.